Welcome to the Electrical and Electronic Engineering lecture series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is the Engineering Lecture Series Self-Test, Part 4. This self-test, Part 4, will be on electric circuits, electromagnetism, electrostatics, single phase, alternating current, and circuit theorems. So follow me in the engineering lecture series by subscribing to my YouTube channel at https://youtube.com/@NdinechiMichael.c. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. To learn more about the topics that the self-test Part 4 covered, please go to my YouTube channel and check out Modules 010 Part 1 and 2, Module 020, Module 021, Module 025 Part 1 and 2, and Module 033. If you do, it will help you to follow more in this self-test so that you will really see how it will help you to understand better the lectures. So this self-test is going to be self-test and lecture at the same time, because as we choose an option, we will be able to explain why that option is the right answer. So question 1 says, which of these is not a good laboratory practice? Because our lecture or the topics we covered here involve being in the laboratory to do some experiments. We are starting this our self-test with the laboratory practice to see how you will play safe while you are studying electricity and electricity-related subjects. So, question 1 says, which of these is not a good laboratory practice? A, you have to plan your job, the job to be done. B, you have to set out the workbench in a neat and orderly manner. C, you have to remove any extraneous items. And D, you must put on jacket. So you see that the answer is D. There is no rule of thumb whether you will put on jacket or not. But if you're putting jacket, you must make sure that it is well tucked in so that it doesn't fly up and down. But A is a good laboratory practice. You must plan the job you want to be done. You must set out the workbench in a neat and orderly manner. You must remove any item that is not to be used in what you are doing. But whether you put on jacket or not, it doesn't matter really. So 2, which of the following statement is incorrect? A, loose clothing should be anchored. Of course, loose clothing should be anchored. Do not wear loose clothing at all. There's no rule of thumb that says you should not wear loose clothing. But like we said, you must tuck them in. Line voltages should be isolated from ground. Very important to avoid shock. And D, You measure voltages with one hand in your pocket. So which one is incorrect? See that your answer is B. No person that says that you should not wear loose clothing. But what you are saying is, when you wear loose clothing, you have to make sure that it is well tucked in. 3, say, in case of accident in the laboratory, the first thing to do is A, report the incident or the accident to the instructor. B, shut off power supply immediately. C, call in a physician. D, administer first aid. So what is the first thing you do? We made it clear that the first thing you do when an electric accident occurs in an electric lab is to shut off power supply so that other people will not be affected. That is the first thing to do before you report the accident to anybody. And of course, when you are in a laboratory environment, you must note some, points where power should be switched off immediately there is any form of accident. Well, which of these is not a first aid practice? A, injured person should be kept warm. That is a practice. Injured person should be kept lying down. Again, a good practice. Injured person should be given water if unconscious. Of course, not true. And injured person should be kept comfortable and cheerful. Our answer is C. Injured person should be given water if unconscious. Is not a good first aid practice. The practice is that if somebody is injured and is unconscious, no form of liquid should be administered on the person. That is stipulation of first aid. Now, one of these is recommended artificial respiration technique. A, mouth-to-mouth breathing. B, mouth-to-nose breathing. C, nose-to-nose breathing. D, nose-to-mouth breathing. Our answer, of course, is A. Say, if accident occurs in the lab and there is need for artificial respiration, one of the techniques applied is mouth-to-mouth breathing. 6, the current in a fixed resistor is A, indirectly proportional to the voltage. B, directly proportional to the voltage. C, inversely proportional to voltage. And D, directly proportional to the square of the voltage. So that's B as our answer. If you recall, when we were treating the Ohm's law, we said that the current in the resistor is directly proportional to the voltage. If you look at the question, in a fixed resistor, V is equal to IR. So I is equal to V over R. So if V is the numerator and fix R the denominator, it means that if V is increasing, I is automatically increasing. And we say that the current in a fixed resistor is directly proportional to the voltage. So answer is B. If the voltage across a resistor is held constant, the current in that resistor is, say, A, directly proportional to its resistance, B, inversely proportional to the square of the resistance, C, directly proportional to the square of its resistance, and D, inversely proportional to its resistance. You say our answer is D. Just like we explained earlier, V is equal to IR. So if you make V, which is the voltage, constant, then the current will be decreasing as the value of resistor increases. And if the value of the resistor is decreasing, the current will be increasing. So you see that it's an inverse proportion. So we say that the voltage across a resistor, if held constant, the current in that resistor is inversely proportional to its resistance. 8. The formula which gives the mathematical relationship between I, R, and V in a closed circuit is what? So it's giving us V equals IR, I equals VR, R equals IV, and V equals IR plus K. So we know that by Ohm's law, that the relationship between voltage, current, and resistance in a circuit is giving us V equals IR. There is no K. That is why D is not our answer and A is our answer. There is no constant. Again, 9, the law that relates I, V, and R in an electric circuit is called what? Say Lenz's law, Coulomb's law, Maxwell's law, Ohm's law. Of course, we know that it is Ohm's law. This is as common and as easy as ABC. So, if the voltage across a 10K resistor is 220 volts, the current in that resistor should be what? Say A, 45.5 amp, B, 4.55 amp, C, 0.022 amp, and D, 0.22 amp. Say that our answer is C. How did we get C to be our answer? Say if the voltage across a 10 kilo ohm resistor is 225, the current should be equal to what? V over R, which is 220 over 10,000. If you do that division, it will give you 0.022 amp, which is C. Now I say the formula which gives the total resistance of two resistors connected in series is giving us what? A, R total is equal to R1 plus R2 plus R3. B, R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. C, R1 times R2 times R3 all over R1 plus R2 plus R3. And D, R1 plus R2 plus R3 all over R1 times R2 times R3. So see that when resistors are connected in series, you just add up the resistances to give you the total resistance in the circuit. So our answer is A. R total is equal to R1 plus R2 plus R3. So 12, the root mean square value of sine wave, of a sine wave is what? A, 3.14, B, 0.707, C, 80, D, 1.00. So our answer is B. When we are looking at root mean square, the RMS value of any sine wave, we multiply the peak value by 0.070. This 0.707 is known as the 3 dB point of that sine wave. And the meaning of that RMS square to the layman's understanding is that when you build a filter that lies within the 0.707 of the maximum value, you will be able to recover all the information in that signal. So we call it root mean square of the sine wave by multiplying that peak of the sine wave, that's the maximum value, by 0.707. And I'm just giving the significance of it, that it helps you to recover the information contained in that signal totally. So you call it the root mean square. So when you are dealing with electrical signals, anytime you hear root mean square, you know that it is multiplying the peak of the signal with 0.707. And what you are doing is that when you do that, all the information about signal will be contained, and if you filter it out, you will recover all the information. So again, 13, the induced EMF in a coil is given as A minus L dV dt, B L dV dt, C minus L di dt, and D L di dt. Well, our answer is C. It is very important for you to note some of these things, because it's something you will meet over and over and over. So it is always good that you know them, that the induced EMF in any coil is given as minus L di dt. The maximum value of the applied voltage in an inductive circuit is A, 2 pi Fc Im. Im means I max, the maximum value of I. B, 2 pi Fc, C, 2 pi Fl, D, 2 pi Fl I max. So our answer is D. When you apply a voltage to an inductive circuit, of course, inductive circuit is represented by letter L, capital letter L. So it's, the voltage will generate, form of current passing through the coil. So because every inductive circuit is assumed to have a coil that is an inductor. So, and it's a function of the frequency of operation of the signal you are passing and the maximum current that is generated in the inductive circuit. So the value of the maximum applied voltage could get as high as 2 pi f L I N, where L stands for the inductor value in Henry, F, the frequency of operation, and Im is the maximum current value. So 15, the inductive reactance of any circuit is given as 2 pi Fc, 2 pi Fi, 2 pi Fl, and 2 pi Fv. Automatically, we know that the answer is C, because we are talking of inductive circuit, and when we talk of inductive circuit, we are talking of inductor being in the circuit, and that inductor being in a circuit is represented by capital letter L. So C, which has L times 2 pi F, is the inductive reactance. So C, the induced EMF in a capacitor is E equals Vm sine 2 pi Ft. When we say Vm subscript m, we are talking of the maximum value. And when we add the sine component of it, automatically we are talking and saying that it is a sinusoid. And the sinusoid starts from the origin. The difference between a sine wave and a cosine wave is that at point zero, sine wave is zero. It starts from the origin. But for cosine wave, at point zero, it is maximum. So that is the difference. But all of them, both cosine and sine wave, are alternating current, alternating wave. So the induced EMF in a capacitor, we have seen that of an inductor. The induced EMF in a capacitor is given as, says A equals Vm sine 2 pi Ft, B E equals C dV dt, C E equals C di dt, and D equals Vm cos 2 pi Ft. So our answer is B. If you recall, when we were looking at electrostatics, so that the voltage developed across a resistor is C dV dt. That is the capacitance multiplied by the rate of change of voltage with time. That is the meaning of that C dV dt. Now, a circuit is said to be in resonance. Circuit is said to be in resonance if the inductive reactance minus capacitive reactance is equal to 1. No. If the inductive reactance plus capacitive reactance is equal to 1. No. If the inductive reactance minus the capacitive reactance is equal to 0. Yes. The other option, inductive reactance plus capacitive reactance is equal to 0. Our answer is C, because we say that inductive reactance equals capacitive reactance. When that happens, the circuit becomes a resonant circuit, which if you say the left-hand side inductive capacitance is equal to the right-hand side, the capacitive reactance, it means that if you cross the capacitive reactance to the left, it becomes inductive reactance minus the capacitive reactance equals 0. So our answer is C. Now, which statement is correct? Energy is stored as electrostatic energy in the capacitor. Energy is stored as electrostatic energy in the capacitor. Energy is stored as magnetic energy in the capacitor. Energy is stored as magnetic energy in the resistor. Of course, our answer is A. Recall that in a capacitor, you have energy stored as electrostatic energy, while in the inductor, you have energy stored as magnetic energy. So, from the options, you can see where C says energy stored as magnetic energy in the capacitor instead of inductor. That is why C is not the correct answer. And of course, the resistor doesn't store magnetic or electrostatic energy. While B is saying that energy stored as electrostatic instead of magnetic in the inductor. So C is magnetic energy capacitor, which is not true. B, electrostatic energy inductor, which is not true. D is out of it, while A is energy stored as electrostatic energy in the capacitor. That is the correct option. So again, the magnetomotive force per meter length of a uniform cross-sectional area of a magnetic circuit is termed magnetic flux density. Do you agree? Magnetic field strength, permeability of free space, hysteresis of the circuit. Of course, our answer is B. The magnetomotive force per meter length of a uniform cross-sectional area of a magnetic circuit is termed magnetic field strength, which is represented by letter H. If you treat similar thing in electricity, we call it electric potential, which is letter E, capital letter E. So you see that whatever you treat in electric circuit, you can treat in magnetic circuit. So for the electric circuit, this potential is represented as electromotive force, which is E. In magnetic field, magnetic circuit is represented as magnetic field strength, which not always you mention that, you just put letter H. And if you're looking at letter H in magnetic circuit, automatically you are talking about magnetic field strength. Now, so which statement is incorrect here? A, so whenever flux linkage in a circuit is changed, there is an induced EMF. When an EMF is induced in a circuit, the self-inductance is proportional to the rate of change of flux linkage within the circuit. Remember, the question is, which one is incorrect? The complete closed path followed by any group of lines of magnetic flux is referred to as magnetic circuit. And D, in magnetic circuits, the magnetic flux is due to the existence of an electromotive force, EMF. Now, let's look at that. From A, when a flux linkage in a circuit is changed, there is an induced EMF. That is correct. When an EMF is induced in a circuit, the self-inductance is proportional to the rate of change of flux within the circuit. Yeah, because B, we are talking of self-inductance. Remember, when we treated inductance, we have self-inductance. If all the flux emanating is linked within the same circuit, we call it self-inductance. If some of the flux linked to another circuit, we call it mutual inductance. So part of will be in the originating coil, while some will cross over to the other coil. That one that crosses over to the other coil, we say it gives rise to mutual inductance, but the one that remain only in the coil that generated it, we say self-inductance. So that self-inductance is proportional to the rate of change of flux linkage within that circuit. And C, so the complete closed path followed by any group of lines of magnetic flux is referred to as magnetic circuit. Yes. If you put a coil, you normally see dotted lines. Each of those dotted lines must go around, maybe in form of ellipse, and close up. So you see, it's a closed path. Magnetic flux doesn't move zigzag. It goes in a closed circuit. So we say when that flux is followed by a group of lines, in most of our lectures, we represented it with dotted lines. Call them magnetic circuits. And D, why D is not correct is that he says in magnetic circuits, and he talked about electromotive force. In magnetic circuits, you will talk about magnetomotive force and not electromotive force. That is what makes D not correct. If indeed we had said in magnetic circuits, the magnetic flux is due to the existence of electromagnetomotive force, MMF, D could have been correct, but because it carefully put electromotive force in a magnetic circuit, that is what makes D to be an incorrect statement. It's proper we get to know these details. Now, the magnetic field strength required to wipe out the residual magnetism is termed what? Magnetomotive force, hysteresis force, coercive force, remanence force. Of course, our answer is C. When we treated, hysteresis loop, we talked of if you energize a magnetic material and de-energize it, it follows another route altogether to return. At the cross where you have the magnetic field strength, there is, a difference between where it started and where it is returning to. So for you to bring the thing back to zero, you have to apply a coercive force. So that is why C is the answer. There is also nothing like hysteresis force, and magnetomotive force is, of course, what as we have explained. Now, what type of capacitor is used for high frequency applications? Recall, we treated some types of capacitors. We talked of A capacitors, paper capacitors, polycarbonate capacitors, and mica capacitors. And we made it clear that mica capacitors are used for high frequency operations and high frequency applications. Now, other ones we follow, we will see as we go down. The force of attraction or repulsion, between two charged bodies is proportional to the magnitude of their charges and inversely proportional to the square of the distance between them. This represents Boas-Savart law. You may recall that in your 100 level physics, you met Boas-Savart law. B, you meant Lenz's law. C, you have also listened to Coulomb's law. D, you may not have talked about Maxwell's law, but very soon you will come to also analyze Maxwell's law. So our answer is C. The force of attraction or repulsion between two charged bodies is proportional to the magnitude of their charges and inversely proportional to the square of the distance between them. If you recall your Gauss law, it says F is equal to K Q1 Q2 over R squared, where R squared is the distance between the two charged particles, and Q1 is the test charge, and Q2 is the next charge. So the distance between two of them over is R squared. So the force between two of them will be given as K, where K is the constant. As we go on, we see the value of K. I don't want to say it here because it is an option in a coming question, so that we'll be able to, answer it with free mind. So, Gauss' theorem states that electric field strength E is force per unit charge. Remember your Gauss law. Electric flux density D is defined as electric flux per unit normal area. The integral of flux density over a closed equipotential surface must be equal to the enclosed surface. That looked very close. The total electric flux passing through a closed surface is numerically equal to the electric charge enclosed by that surface. The answer is D. If you look at C and D, the difference is not much, but it talked about C talked about closed equipotential surface, while D talked about closed surface and says numerically equal. So when you are listening or getting to know Gauss theory, two things are important that you must see. Closed surface, numerically equal electric charge. So if you don't see it, these three things, then that thing is not describing the Gauss theorem. Now, 25. The work done by an extraneous force against the force of the electric field in moving a particle bearing a unit charge from one point to another is known as what? Is it potential difference? Is it electric potential? Is it permittivity of the medium? Is it permeability of free space? Of course, the work done in our lecture, we even try to demonstrate it by drawing a small line to show it, that the work done by an external force, when we say extraneous force, the external force, against the forces of the electric field in moving a particle bearing a unit charge from one point to another is known as electric potential. There is difference between electric potential and potential difference. Please note that. Then, so what is the equivalent capacitors the equivalent capacitor of three capacitors with values 100 microfarad, 500 microfarad, and 300 microfarad connected in series. Gives options 900 microfarad, 652 microfarad, 65 microfarad, and 300 microfarad. Of course, when you are working for capacitors in series, it's different from what you have seen about resistors in series. It becomes 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3. So if you do that, 1 over 100 plus 1 over 500 plus 1 over 300, if you get the answer, you'll find the inverse of it. That will automatically give us 65 microfarad. On the other hand, when we want to find the equivalent of capacitors in parallel, like in 27, say the equivalent of capacitors 10 microfarad, 50 microfarad, and 30 microfarad connected in parallel. So it gives answer 90, 65, 30, 6.5. They say our answer is A. Now, there is something to deduct here. If you look at question 27, you see that the values of the three capacitors are smaller than the values of the three capacitors in question 26. But the answer of that of 26 is 65 microfarad, while that of 27 is 90 microfarad. So you see, if you have resistors, capacitors available to you for some work, and you needed a lower value to do or achieve what you are doing, you connect those capacitors in parallel to get higher value. If you connect capacitors in parallel, the equivalent will be higher. If you connect them in series, the equivalent will be lower. That is just what we want to bring out here, because when you are doing your electrical design, you may not have the exact value of capacitor or resistor you want to use. Then you may have to connect them in series or parallel to achieve what you want. So when you are dealing with resistor, the reverse is the case. If you are looking for higher value, you connect in series for resistors. If you are looking for higher value for capacitors, you connect in parallel. So that should form a rule of thumb for you to know and understand. 28. Any individual circuit component with two terminals by which it can be connected to other electric components is called A, branch, B, circuit element, C, electric network, and D, electric circuit. Of course, we made it clear that when we were defining that it is circuit element, any individual component with two terminals, like resistors, capacitors, inductors. They are called circuit elements. So now, 29, three resistors, R1 equals 220 ohms, R2, 330 ohms, R3, 1 kilo ohm are connected in parallel. What is the equivalent resistance of the circuit? Say 117, 1550, 551, 1000. So the answer is A, 117. So you can see higher capacity, higher resistors, 220, 330, 1 kilo ohm When they are connected in parallel, the equivalent becomes just 117, lower than any of them. You can now use it to, look at what we talked about when we talked, about capacitors. So that will, give you information on when you carry out your design and you are looking for a smaller value of resistor. Then you bring higher values, connect them in parallel to get lower values. Now, which of the statements is incorrect? A current source is a generator which maintains its value of potential independent of the output current. B, a current source is a generator which maintains its output current independent of the voltage across its terminal. And C, a circuit element is linear if the relationship between the current and the voltage involves a constant coefficient. D, an active network contains energy sources together with other current elements. Say our answer is A. Which one of the statements is incorrect? A current source is a generator which maintains its value of potential independent of the output current. It's not correct. It's an incorrect statement. So a body or an individual atom of that body is said to have an electric charge when it acquires excess or is deficient in electrons. True or false? Of course, it is true. When a body acquires excess, when it acquires excess or in deficient of electron, we say that statement is true because whichever way, if it is in excess, some moves to form a bond with the other one, with the other atom, and that constitutes electric charge. If it is deficient, another from the other one comes and still becomes movement of electrons. So when that happens, you now say that electric charge is in the circuit. So our answer is true. Probably next time we introduce some basic electronics so that we can, get this very well. So when there are surplus electrons, the body is said to be positively charged, actively charged, negatively charged, or neutrally charged. Of course, we say that it is negatively charged. When there are surplus electrons, we say that the body is negatively charged. It's important that you note some of these things and commit them to memory. So a body is positively charged if there is excess of electrons, if there is deficiency of electrons, sorry, not electronics, B, deficiency of electrons, not electronics, please. If it has no atom, and D, if it is neutral. Don't mind the typo in this number. C is if it has no atom, and D is if it is neutral. So the answer is B. A body is positively charged if there is deficiency of electrons. Know that. Electrons, not electronics. Electrons carry positive charge. So if there is deficiency of it, say it's positively charged because you see those circles with pluses inside. Now, which of the equations below represents the Coulomb's law? A, F equals QE. Remember, we defined Coulomb's law before. B equals 1 over 4 pi epsilon. The epsilon is the permittivity of a free space. C equals 10 raised to power minus 9 over 36 pi. D, F equals K Q1 Q2 over R squared. Without being told, we know that D is the answer, because when we were defining Coulomb's law, we say that it is K, F equals K Q1 Q2 over R2 squared, where R is the distance between charge 1 and charge 2, and K is the constant, which is given as the value in B. Answer is D. 35. The electric field strength E is defined as displacement by Maxwell, force per unit charge, electric flux density, electric flux per meter normal area. Our answer is B, force per unit charge. So E is equal to F over Q. We have seen, okay, in our lecture model 10, we have defined that E is equal to F over Q, force per unit charge. Now, if applied electricity, in applied electricity, which of the letters represent the electric flux density? H, B, D, E. Of course, we know that it is D that represents that. So our answer is C. In applied electricity, the letter representing electric flux density D, which we said is defined as displacement by Maxwell. Now, H, we said, is the magnetic flux density. E is the electric potential. And B is also a term which we call the magnetic flux. So you see, H and B is equivalent of D and E. In H and B is in magnetic circuits, D and E are in electric circuits. Of course, we know that there is more difference between analysis of electric circuits and magnetic circuits, which we have already treated in I think module 10 of our lectures, or thereabout, or 20. Now, capacitance is defined as the ratio of the charge on a conductor to the applied voltage when all the neighboring conductors are at zero potential. True or false? True. You know that capacitance C is the ratio of the charge on the conductor to the applied voltage. We will say that C is equal to Q over V. Now, which of these categories of capacitors are stable for varying capacitance in radio sets? In those days, you just use, when you tune your radio, what you're doing is you're varying the capacitance, and as you vary that capacitance, you vary the frequency, and that helps you to select different frequencies which belong to different stations. So say which capacitor is used for that. So mica, air, paper, polycarbonate. So say it's A capacitors. We have seen what mica is used for. So it's left for you to know what paper capacitors do, or the applications of it, and the applications of polycarbonate capacitors. Now, which of these is not correct about electrolytic capacitors? A, the insulator resistance is very high. It's not likely because we say that they operate with low resistance. So B, suitable for circuits where the voltage applied never reverses its direction. C, use where large capacitance is required. D, the insulator resistance is comparatively low. So our answer is A, because we say electronic capacitor is used have very low resistance. But here it's saying that the insulator resistance is very high, which is not correct. The answer is A. Now, which of these laws is associated with the mutual inductance of flux linking a coil? I expect you to know this because it's something you must have met in your 100 level physics. Lenz's law, Maxwell's law, Faraday's law, and Newton's law. If you don't know all about these laws, then you have to go back a bit to, look at your 100 level physics. So answer is C. It is Faraday's law that talks about mutual inductance. Lenz's law talks about self-inductance. And of course, we know Newton's law talking about laws of motion. And of course, Maxwell's law talking about electromagnetic waves. Now, which of these statements is correct? A circuit has a self-inductance of 1 Henry when an EMF of 1 ampere is induced by a rate of voltage change equal to 1 volt. A circuit has a self-inductance of 1 Henry anytime an EMF of 1 volt is applied. A circuit has a self-inductance of 1 Henry when the rate of current change is equal to 1 ampere. A circuit has a self-inductance of 1 Henry when an EMF of 1 volt is induced by a rate of current change equal to 1 ampere. So the answer is D. That is the definition of self-inductance. Remember, I've explained that there's a difference between self-inductance and mutual inductance. And self-inductance is what Lenz is talking about, while Faraday is talking about mutual inductance. Now, the ratio of flux density B at a point to the magnetic field strength H at that point is termed what? Permeability, B, permittivity, C, mutual inductance, D, self-inductance. Of course, we know that it is permeability. When you are talking about flux or magnetic circuits, you talk about permeability, which is represented by mu. When you are talking of electric circuits, you talk about permittivity, which is represented by epsilon. So it's important for you to know that, because this 42 is talking about flux density and magnetic field strength. So it's purely talking about magnetic circuit, which has to deal with the permeability and of any material is given as B over H, which is flux density over magnetic field strength, which we said you must always know. 43, in the hysteresis loop, if the value of H is reduced to 0, the flux density remaining in the ion is referred to as the coercive flux, the residual flux density, the relative permeability, and the absolute permeability. Our answer is B, the residual flux density. The residual flux density, B. So if you go back and look at that plot, this will help you to, know the type of question you'll be expecting from the hysteresis loop plot. So we are getting to the end. In a closed circuit, the algebraic sum of the products of the current and the resistance of each part of the circuit is equal to the resultant EMF in the circuit. This is a statement of the Ohm's law, not true, Kirchhoff's current law, Kirchhoff voltage law, or Thevenin's theorem. So it looked very much like the Kirchhoff's current law and also Kirchhoff's voltage law. So we look at it very critical to now see which exactly is represented. That in a closed circuit, the algebraic sum of the product of the current and resistance. What is the product of current and resistance? V, which is V equals IR. So IR has is I times R, which is a product. So you see that it's talking about the voltage. So what that statement is talking about is therefore the Kirchhoff's voltage law, because it's talking about the product of current and resistance, which is V equals IR. The total current flowing towards a node is equal to the total current flowing away from that node. Is also a statement of what? Automatically, we know that it is Kirchhoff's current law. The answer is A. When you have a node, the total current flowing towards the node is equal to the total current flowing away from the node. So now, 44, in a linear network containing more than one source of EMF, the resultant current in any branch is the algebraic sum of the currents that will be produced by each acting alone, all other sources of EMF being replaced meanwhile by their respective internal resistances. Immediately you hear circuit theorem that talks about replacing sources of voltages, automatically you know it's talking about superposition theorem. So our answer here is C, superposition theorem. When you're talking about replacing sources of EMF, superposition theorem. So you should know also when we are talking about Thevenin's theorem, you also know when we are talking about, even though we have not talked about Norton's and other ones, but you should know. Which of the theorems says that an active network having two terminals and A and B can be replaced by a constant voltage source having an EMF E and an internal resistance R? Automatically, again, we know that it is Thevenin's theorem. That is the two theorems we've talked about, Thevenin's and superposition theorems. Any network in which physically separated resistors, capacitors, and inductors can be represented is called a distributed network, a passive network, an active network, a lumped network. Our answer is D, lumped network. If you have any circuit where you can, just work on values of capacitors, resistors, and inductors, it means you can isolate them. You can separate them separately and see what is happening to them. You call that circuit a lumped circuit. On the other hand, when you can't do that, you call them distributed network. So a network that contains only circuit elements without any energy source is called, of course, a passive network, which is answer B, passive network. Then any network in which resistors, capacitors, and inductors cannot be electrically separated and individually isolated as separated elements is called what? A lump circuit, we have seen what a lump circuit is when you can separate them. A nonlinear network, a nonlinear network is when the left-hand side is not easily determined by the right-hand side. C, a distributed network, of course, that's the answer. D, an active network. No. So our answer is C, distributed network. And we say that this distributed network is, used for transmission lines. A transmission line is an example of a distributed network, D, because you cannot separate the inductor, the capacitor, and the resistor, even though they all exist in a transmission line. Maybe as you go on, we will also talk about two-port networks that will give us clear understanding of transmission lines, and when we apply it to develop our antenna principles. So, 52, I think that's the last. The node voltage analysis of circuits employs the Kirchhoff's voltage law. True or false? The answer is false. The node voltage analysis employs the Kirchhoff's current law, while the mesh voltage analysis makes use of the Kirchhoff's voltage law. So, which of these statements is incorrect? Kirchhoff's current law is the basis of mesh analysis of networks. Kirchhoff's voltage law is the basis of mesh analysis of electrical network. A mesh is a closed circuit path that does not cross any other path. A loop may have other loops or meshes inside it. The answer is A. If you look at the past one we did, that Kirchhoff's current law is the basis for the mesh analysis. So thank you for going through the self-test in the engineering lecture series with me. It is going to be more regular from now on. As we do our lectures, we do self-test on it. It will assist you to evaluate your understanding of the topics already treated. Now, before we go, I want you to look at this. Say, there is some likelihood of joy and happiness in being mad, only that the same ones do not know how to find out. Please do not try to find out, because it's not all about madness. But as a student, if you see people who don't take delight in reading their books, in studying their, whatever, you look as if they are happy and joyous in doing that. Please don't try to join them, because if you join them by not reading and studying hard, you may not like the outcome. So he said, please do not try to find out how people that didn't study very hard, how they feel when the results come out and they have low grades. So that is my advice to students. So it is not just about being, mad, but not doing the right thing. By the time you find out the consequence of not doing the right thing, it may be too late for you to change. That is my advice to my students. Thank you for listening, and see you later. Thank you.